Project critical path is basically a visual trajectory of the critical project activities through a project network diagram that result in a feasible project duration. While one cannot address the subject of the project critical path without the project network diagram, the two are intertwined, or rather the project critical path is located within the project network diagram. While a project critical path can also be addressed and determined by way of a project schedule, but it is better explained and illustrated by way of a project network diagram. In this video, even though the focus is the critical path, but the network diagram is covered extensively. To make it comprehensible, we start by addressing the project critical path by employing a simple illustration that is basic, that doesn't employ the critical path method fully. This is to ensure that the critical path concept makes sense fundamentally. Then once this is achieved, we then take it one notch higher by addressing it fully through the critical path method or through the critical path analysis. This entails the employment of the forward pass analysis and the backward pass analysis. These are planning aspects that a project manager cannot escape when planning and leading larger or complex projects. Well, according to the PMI's PMBOK, project critical path refers to the sequence of project activities that represents the longest path through a project, which determines the shortest possible project duration. But remember, we said that project critical path is fundamentally a visual trajectory of the critical project activities through a project network diagram that result in a feasible project duration. By feasible project duration, I mean the minimum practical and the minimum predictable amount of time that it would take or could take to start and to finish a specific project. Whereas critical project activities are those project activities that should be treated as critical in terms of their durations. Their durations cannot be compromised or delayed without compromising or delaying the feasible project duration, or without compromising the ideal or the optimum project time. Project network diagram, on the other hand, is a schematic view or picture of how project activities in a project logically flow from the first to the last, or how they practically and logically precede and succeed each other. That is, project network diagram is a visual demonstration of which project activities have to start and finish before other activities can start. It is a visual demonstration of the dependency relationship between project activities in a project. Well, according to the PMI's PMBOK, a project network diagram, actually the PMBOK refers to it as a project schedule network diagram. According to the PMI's PMBOK, a project schedule network diagram is a graphical representation of logical relationships that are also referred to as dependencies among the project schedule activities. The logical flow of project activities, or rather the logical linkage or connection of the project activities in a network diagram, is not linear, but it is a function of project activities, precedence, dependency, and logical sequence. It is not a straight line, but it is a network. It is a web. It is a mesh with each linkage or connection being a function of the dependency between and among the project activities. As you can see in this schematic view, activity 1 has to start and finish before activity 2 and activity 3 can start. That is, both activity 2 and activity 3 have an activity 1 dependency. Also, activity 4 can only start after activity 3 has finished. Activity 5 likewise can only start after activity 4 has finished. And interestingly, activity 6 has two dependencies, and those are activity 2 and activity 5. That is, activity 6 can only start after both activity 2 and activity 5 have finished. If one activity between activity 2 and activity 5 finishes earlier than the other, say activity 5 finishes a day earlier than activity 2, activity 6 will have to wait until activity 2 finishes before it can start. Activity 7 has a dependency on activity 2. It can only start after activity 2 has finished. Whereas activity 8 has both activity 6 and activity 7 as its dependencies. That is, both activity 6 and activity 7 have to start and finish before activity 8 can start. Lastly, activity 9 has an activity 8 dependency. Activity 9 can only start after activity 8 has finished. In a project of building a house, the construction of the house foundation precedes the construction of the house walls. The commencement of the activity of building the house walls is dependent on the start and the finishing of the activity of constructing the house foundation. Logically and practically, the house walls building activity cannot start and cannot even happen before the activity of building the house foundation has been completed. Such a relationship or such a logical and practical dependency between and among the project activities is applicable to all types and all sizes of projects. Just as a recap, project critical path is basically a visual trajectory of the critical project activities through a project network diagram that result in a feasible project duration. Remember, we said that the critical project activities are those project activities that should be treated as critical in terms of their durations. That their durations cannot be delayed without compromising the feasible project duration, or without causing an impairment to the ideal or to the optimum project time. As you can see in this schematic view, the 9 activities of this project have durations, where activity 1 has a duration of 1, implying that it will take a single period for activity 1 to finish after starting. Let's just use days as the periods for this example. Therefore, that implies activity 1 will take 1 day to finish after starting. And activity 2 will require 6 days to finish after starting. Whereas activity 3 will require 2 days, and so forth until activity 9 that requires 1 day to be executed. The critical project activities through this network are activity 1, activity 2, activity 6, activity 8, and activity 9. And the sum total of their individual durations adds up to 14 days, which is the total duration or the feasible project duration of the project represented by this network diagram. The determination of the individual project activities' durations is not adequate to use in determining the total project duration. Due to the complexity brought about to the project work by the sequencing and dependencies among project activities, the durations of project activities are not simply added up together to determine the total project duration. Instead, the durations of parallel or concurrent activities are represented by the longest activity of those parallel or concurrent instances. The project management technique that addresses this issue of parallel or concurrent activities is referred to as the critical path method, shortened as CPM, It is also referred to as critical path analysis, that is shortened as CPA. As you can see in this schematic view, there are two paths between activity 1 and activity 6. One path is through activity 3 and activity 4 and activity 5, equaling 5 days. The other path is through activity 2, equaling 6 days. And therefore, the path that goes through activity 2 is the most feasible because it is the longest, or rather it is longer than the activity 3, activity 4, activity 5 path. That is, it is not feasible, it is not practicable, and it is not workable to start activity 6 after the activity 3, activity 4, activity 5 path. The project still has to wait for activity 2 to finish before it can start activity 6. Similarly for activity 8. Activity 8 cannot start before activity 6 is finished, even though it also has a dependency on activity 7, which can finish earlier than activity 6. Therefore, the activity 6 route is more feasible for activity 8 to start than the activity 7 route. Now let's bring this nearer home by considering a more practical example. But I think that with this brief background and with the discussion that we have just had, I think it will now be easier to compute or to determine a project critical path using a practical project example. It will now be easier to slot in other factors and other sub-processes that are necessary in the determination of a project critical path and consequently the determination of a feasible project duration. So far in the previous example, we have considered only two attributes of each project activity. The first attribute being the duration of a project activity, and the second being the name or the description of a project activity, even though we've used pseudonames or pseudo descriptions. But going forward, we will allocate real-life and practical project activity names or descriptions. In more complex projects, it is necessary to consider other project activity attributes in a project network diagram in order to arrive at an optimal project critical path and at an accurate, feasible project duration. These project activity attributes are the early start, the early finish, the late start, the late finish, and the float values for each project activity in a project network diagram. This is done and achieved by utilizing a project management technique referred to as the project critical path method. This technique uses the forward pass analysis and the backward pass analysis to determine the values of these project activity attributes. The critical path method is a project management technique that is used to determine a project's critical path and a project's feasible duration. This is done by first executing the forward pass analysis and thus determining the early start value and the early finish value for each project activity on the project network diagram. And second, by executing the backward pass analysis and thus determining the late start value and the late finish value for each project activity. And third, by determining the float value or the slack time value for each project activity on the project network diagram. And fourth, by determining the project's critical path by following an unbroken trajectory of all the project activities with zero float value in the project network diagram. According to the PMI's PMBOK, the critical path method is used to estimate the minimum project duration and to determine the amount of schedule flexibility on the logical network paths within the schedule model. This schedule network analysis technique calculates the early start, the early finish, the late start, and the late finish dates for all activities without regard for any resources limitations by performing a forward and backward pass analysis through the schedule network. While early start refers to the earliest time, or hour, or day, or week, or month, depending on the project duration time unit on which a project activity can start. It refers to the earliest time on which a project activity can start, whereas early finish refers to the earliest time that a project activity can finish. Late finish refers to the latest time that a project activity can finish, so it does not increase overall project duration. Late start refers to the latest time that a project activity can start, so that it does not increase overall project duration. Float or slack time is the amount of time that a project activity can be delayed by without causing any of its successor project activities to be delayed. Put more broadly, it is the amount of time that a project activity can be delayed without causing the entire project to be late. The difference between the early start and the early finish for each project activity is its duration. And the difference between the late start and the late finish for each project activity is also its duration. It is impossible to start a project activity before its early start date because it is dependent on its predecessor activities. Also, finishing a project activity after its late finish becomes detrimental to the start of its successor activities and thus messes up the timing of the rest of the project activities and eventually the total project time or the feasible project duration. Before delving into determining the early start, early finish, late start and late finish and float, that is before discussing the forward pass analysis and the backward pass analysis, let us consider a real-life or a practical project as an example. Let us consider a project that is undertaken to build a custom steel gate. Our example of the custom steel gate building project has 24 activities. And through, say, expert judgment, we have allocated durations to all the 24 activities. We have also established the dependencies or predecessors for all the activities. As you can see, that activity 2, which is major site gate, has activity 1, which is receive custom gate order as its predecessor. Also, activity 3, which is sketch the custom gate drawings, has a dependency of activity 2, which is major site gate. Activity 18, weld steel components into a steel gate structure, has 2 dependencies, and these are activity 14 and activity 17, which are the order or purchase welding rods activity, and the cut steel into components for the steel gate structure activity respectively. Please note that in project management, and particularly in project time management planning, some project activities are referred to as events. And an activity that is regarded as an event has 0 duration. An event in project management is either a significant symbolic point or an instantaneous activity that doesn't warrant an allocation of time or duration. Significant symbolic point, usually referred to as a milestone in project management, is a point in a project time management plan, be it in a project schedule or in a project network diagram. It is a point in a project management plan that symbolizes a significant event. Examples of such includes the start of a project, that's an event. The end of a project is also an example of an event. The start or the end of a project phase, such as the completion of a house foundation in a project of building a house, is also an event. According to the PMI's PMBOK, a milestone is a significant point or event in a project. Milestones have zero duration because they represent a significant point or event. As you can see in our example of a project of building a custom steel gate, the activity of receiving the custom gate order from the customer and the handing over of the completed custom gate to the customer are milestones. They are significant symbolic points in the project. So are the activities of approving the gate design sketches and the activity of transporting the custom gate to site are instantaneous activities that do not warrant an allocation of time or duration. Hence, they allocate zero durations because they are regarded as events. These 24 activities of the example of the custom steel gate building project can be easily plotted into a project schedule, using each activity's duration and dependency to do so. Project schedule is addressed, covered, and discussed in more detail in a video on project management planning on this Real Institute channel. Using the dependencies of the project activities, we can then construct the project network diagram for the custom steel gate building project. You'd recall that project network diagram, on the other hand, is a schematic view or picture of how project activities in a project logically flow from the first to the last, or how they practically and logically precede and succeed each other. That is, project network diagram is a visual demonstration of which project activities have to start and finish before other activities can start. It is a visual demonstration of the dependency relationship between project activities in a project. As you can tell, we have summarized and acronymed some of the names or descriptions of the project activities. We can then also proceed to allocate the durations to all the project activities in the network. Now we can perform the forward pass analysis and the backward pass analysis to determine the early start, the early finish, the late start, the late finish, and the float values for all the project activities. With the forward pass analysis, for each project activity, we calculate the top attributes, which are the early start value and the early finish value, in a forward direction. That is, from left to right, or from the first activity to the last. Whereas with the backward pass analysis, again for each project activity, we calculate the bottom attributes, which are the late start value and the late finish value, in a backward direction. That is, from right to left, or from the last activity back to the first activity. Then the float or slack time is then calculated last as the difference between the late start value and the early finish value in each project activity. Now, using the forward pass analysis, as you'd recall, we said that early start refers to the earliest time on which a project activity can start. The first rule or the first principle of the forward pass analysis is that the early start of the first project activity in a project network diagram is allocated a value of 0. This is only for the first activity. And then the second rule of the forward pass analysis is that the early start values of the rest of the project activities are the early finish values of their predecessors. That is, we simply move the early finish value of a preceding activity to be the early start value of its succeeding activity or of all its succeeding activities. Also, in a case of an activity that has more than one predecessor, that is, an activity that has more than one dependency activities, then the one with the largest early finish value becomes the early start value of the succeeding project activity. You would also recall that we said early finish refers to the earliest time that a project activity can finish. For each project activity, this is calculated by adding the early start value and the duration value. That is, early finish in each project activity is the sum of its early start value and its duration value. In our example, the early start value of activity 1, which is the receive order activity, is allocated the value of 0. And it already has a 0 duration. And therefore, its early finish, which is calculated from adding its early start value and its duration value, equals to 0. Activity 2, which is the measure site activity, is allocated an early start value equal to its predecessor's early finish value. Its predecessor being activity 1, the receive order activity, which has a 0 early finish. We simply move that 0 to be the early start value for activity 2. And activity 2 already has a duration of 1. And therefore its early finish, which is calculated from adding its early start and its duration, is 1. Because 0 plus 1 equals 1. Activity 3, on the other hand, which is the sketch drawings activity, is allocated an early start value equal to its predecessor's early finish value. Its predecessor being activity 2, the measure site activity, which has an early finish value of 1. We then simply move that 1 to be the early start value for activity 3. And activity 3, which is the sketch drawings activity, already has a duration of 2. And therefore its early finish, calculated from adding its early start and its early duration, is 3. 1 plus 2 equals 3. Activity 4, which is the approved drawings activity, is allocated early start value equal to its predecessor's early finish value. Its predecessor being activity 3, the sketch drawings activity, which has an early finish value of 3. We simply move that 3 to be the early start value for activity 4. And activity 4, which is the approved drawings activity, already has a duration of 0. And therefore its early finish, calculated from adding its early start and its early duration, is 3, because 3 plus 0 equals 3. Activity 5, which is the bill of quantities activity, is allocated early start value equal to its predecessor's early finish value. Its predecessor being activity 4, the approved drawings activity, which has an early finish value of 3. we simply move that 3 to be the early start value for activity 5, which is the bill of quantities activity. And activity 5 already has a duration of 1, and therefore its early finish, calculated from adding its early start and its duration, is 4. 3 plus 1 equals 4. On the other hand, activities 6 to activity 16, from the order or purchase paint activity all the way to the order or purchase track activity, are allocated early start values equal to their predecessor's early finish value. Their predecessor being activity 5, which is the bill of quantities activity, which has an early finish value of 4. As a result, all these order or purchase activities have early start values equaling 4, and their respective early finishes are calculated from adding their early start values of 4 to their respective durations values. For example, activity 10, the order or purchase deco accessories activity, already has a duration of 10, and therefore its early finish, calculated from adding its early start and its duration, is 14, because 4 plus 10 equals 14. Activity 21, on the other hand, that is the finish gate activity, has 4 predecessors, which are the activity order or purchase paint, and the activity order or purchase wheels, handles and locks, and the activity weld steel structure, and the activity order or purchase deco accessories, and is allocated early start value equal to the largest early finish value from all its predecessors. And that value is 14 because the order or purchase deco accessories activities has an early finish value of 14, which is the largest among the 4 predecessors. Activity 21, the finish gate activity, already has a duration value of 4, and therefore its early finish, calculated from adding its early start and its duration, is 18, because 14 plus 4 equals 18. The same logic is carried forth until the last activity, which is activity 24. Activity 24, which is the handover gate activity, is allocated early start value that equal to its predecessor's early finish value. Its predecessor being activity 23, the hang and test gate activity, which has an early finish value of 20. And activity 24 already has a duration of 0, and therefore its early finish, calculated from adding its early start and its duration, is 20, because 20 plus 0 equals 20. Then the forward pass analysis is done, and all the top attributes, being the durations that were already determined earlier, and then the early starts and the early finishes, have been calculated for all the project activities. Now, using the backward pass analysis, you'd recall that we said late finish refers to the latest time that a project activity can finish, so it does not increase overall project duration. The first rule or the first principle of the backward pass analysis is that the late finish of the last project activity in a project network diagram is allocated the value of its early finish that was calculated by the way of the forward pass analysis. This is only applicable for the last activity. And then the second rule of the backward pass analysis is that the late finish values of the rest of the project activities are the late start values of their successors. That is, we simply move the late start value of a succeeding activity to be the late finish value of its preceding activity. Also, in case of an activity that has more than one successor, that is where an activity is a dependency of more than one activity, then the one with the smallest late start value becomes the late finish value of the preceding project activity. You'd also recall that we said late start refers to the latest time that a project activity can start, so it does not increase the overall project duration. This is calculated by subtracting the project activity duration value from the project late finish value within individual project activities. In our example, the late finish value for the last activity, which is activity 24, which is the handover gate activity, is allocated a value of 20, which is basically moving the value of its early finish, which is 20. And then the late start of that last activity is calculated by subtracting its duration value from its late finish value. Its late finish value is 20 and its duration value is 0. And therefore the value of its late start is 20 because 20 minus 0 equals 20. Activity 23, the hang and test gate activity, is allocated a late finish value equal to its successor's late start value. Well, it is its predecessor when going backward, but in reality and in the normal flow of the project network diagram, it is its successor. And therefore we will stick with the successor tag even though we are mindful that we are moving backward. And therefore the successor of activity 23 is activity 24, the handover gate activity, which has a late start value of 20. And therefore the activity hang and test gate is allocated a late finish value of 20. And then its late start value is calculated by subtracting its duration value from its late finish value. Its late finish value is 20 and its duration value is 2, and therefore the value of its late start is 18 because 20 minus 2 equals 18. Activity 21, the finish gate activity, is allocated a late finish value equal to its successor's late start value. And its successor is activity 24, which is the transport gate activity with a late start value of 18. And therefore the activity finish gate is allocated a late finish value of 18. And then its late start value is calculated by subtracting its duration value from its late finish value. And its late finish value is 18 and its duration value is 4. And therefore the value of its late start is 14 because 18 subtract 4 equals 14. Activity 13, which is the order or purchase sand and cement activity, is allocated a late finish value equal to the smallest or the lowest value of its two successors' late start values. It has two successors, and they are the activity set posts with a late start value of 14 and the activity set track with a late start value of 16. And 14 is the lowest of the two. Therefore, activity order or purchase sand and cement has its late finish allocated an amount of 14. And then its late start value is calculated by subtracting its duration value from its late finish value. Its late finish value is 14 and its duration value is 1. And therefore the value of its late start is 13 because 14 subtract 1 equals 13. Activity 5. The bill of quantities activity is allocated a late finish equal to the smallest or lowest value of its 9 successors' late start values. And activity order or purchase deco accessories has the lowest late start value of 4 among the 9. Therefore, the activity bill of quantities has its late finish allocated a value of 4, and then its late start value is calculated by subtracting its duration value from its late finish value. Its late finish value is 4 and its duration value is 1, and therefore the value of its late start is 3 because 4 minus 1 is 3. Same logic is carried forth and until the first activity. The first activity, being the receive order activity, is allocated a late finish value equal to its successor's late start value, and its successor is activity 2, the major side activity, with a late start value of 0. And therefore the activity receive order is allocated a late finish value of 0. And then its late start value is calculated by subtracting its duration value from its late finish value. Its late finish value is 0 and its duration value is 0. And therefore the value of its late start is also 0 because 0 minus 0 is 0. Then the backward pass analysis is done, and the 2 of the bottom 3 attributes, being the late starts and the late finishes, have been calculated for all the project activities. Lastly, calculating the float. Again, as you'd recall, that float or slack time is the amount of time that a project activity can be delayed by without causing any of its successor project activities to be delayed. This is calculated last. For each project activity, its float is calculated by subtracting its early start from its late start. In our example, for the first activity receive order, it has an early start value of 0 and a late start value of 0. Subtracting a 0 from 0 yields a 0. Therefore, it has a float amount of 0. Then activity order or purchase cutting discs has an early start value of 4 and a late start value of 10. Subtracting a 4 from 10 yields a 6. Therefore, it has a slack time of 6. Activity cut steel has early start value of 6 and a late start value of 11. Subtracting 6 from 11 yields a 5. Therefore, it has a float value of 5. The last activity handover gate, has an early start value of 20 and a late start value of 20. Subtracting a 20 from 20 yields a 0. Therefore, it has a float amount of 0. The same logic applies to all the project activities in the project network diagram. Lastly, and this is about determining the project critical path. As we've already stated, that float or slack time is the amount of time that a project activity can be delayed without causing the entire project to be late. It can also be viewed as the amount of buffer time, which is basically a time that is more than the allocated duration that is available to complete a project activity. While buffer time refers to the cushion time or the mitigation time or the fat in the project time. A project activity can only afford to be delayed or started late by the amount or by the value of its float without causing the entire project to be delayed or becoming late in completion. However, the project activities with zero float are the critical project activities. They cannot afford to be delayed or started late by any time, even by 1 day, without causing the entire project to be delayed or becoming late in completion. Project activities with zero float are on the project critical path, and they are the critical project activities. They constitute a visual trajectory through a project network diagram that result in a feasible project duration. The sum total of the durations of the critical project activities adds up to the feasible project duration. In every project, this is the case. In the case of our example, the feasible project duration is 20 days. Project critical path is fundamentally a visual trajectory of the critical project activities through a project network diagram that result in a feasible project duration. And the sum total of the durations of the critical project activities adds up to the feasible project duration in every project. Project critical path method and project network diagram are some aspects of the project time management plan. The project time management planning process is addressed, covered and discussed in its entirety in its dedicated video on this Real Institute channel. You may also subscribe to this Real Institute channel so that, among other things, you may receive notifications of newly published content.